Hi, my name is Reddy, and I'd like to present our recent work on assisted perception, optimizing observations to communicate state. The goal of this project is to help users estimate the state of the world in sequential decision-making tasks like robotic teleoperation and navigation with visual impairments. Consider a visually impaired user trying to navigate a house. They can't directly perceive the scene in front of them. Looking at the house from a bird's eye view, they're trying to reach a position in the middle. They think they're in one corner of the house, but in reality, they're actually in a different corner. This mistake in state estimation can cause the user to move farther away from the goal instead of toward it. So what exactly went wrong with the user's state estimation process? Typically, the user would receive the full image observation, then think to themselves, given the observation I just received and the action I just took, I'm probably now at the following state. This state estimation process takes a history of observations and actions and maps it to a belief distribution over possible current states. After updating their beliefs, the user then takes an action that makes sense to them given where they think they are, for example, turning and walking toward their goal. The problem is that the user may have perception difficulties or systematic biases that prevent them from making use of that full observation, which in turn prevents them from accurately estimating the state and then taking an optimal action for their desired task. Users can have trouble processing observations for a variety of reasons, like not being able to pay attention to many different sensors at the same time, or lens distortions causing them to overestimate distances to objects, or even optical illusions affecting the user's biological vision system. The roller illusion you see here seems to be animated, but it's actually just a static image. The key insight in this work is that true, full observations are not necessarily the most informative about the state, especially when they're processed incorrectly by the user due to systematic biases in perception. We operationalized this insight by using an automated assistant to process the full observation on behalf of the user. This assistant performs state estimation unencumbered by systematic biases or perception difficulties that the user may have. Then the assistant provides the user with a different, modified observation that is more accessible to the user than the full observation. The user then takes this modified observation and performs state estimation using their potentially suboptimal process. We call this method assistive state estimation, or ACE. The ultimate goal of ACE is to make the user's belief match their true state. One challenge with this approach, though, is that the assistant doesn't necessarily know the true state, so we settle instead for trying to make the user's beliefs match the assistant's beliefs. Formally, we try to minimize the KL divergence between the assistant's beliefs and the user's beliefs. After the assistant processes the true observations, it synthesizes a modified observation that it thinks will make the user believe in the same state as the assistant. The main challenge with this approach is that we don't have access to the user's internal state estimation process. We address this problem by learning a model of the user's belief update from demonstrations of user actions. We start with an initial model of the user's state estimation process that makes some assumptions about the user's systematic biases and perception difficulties. We then use this initial model to assist the user and record the actions that were taken by the user while they were being assisted. Because the initial model may not be accurate, even with assistance, the user may still take suboptimal actions. Then, after the episodes are completed, we ask the user which tasks they were trying to perform in those episodes. For example, we ask them which goal states they were trying to reach. This enables us to compute the optimal policy for the tasks, and then to fit a new user model that explains the gap between the optimal policy and the user's suboptimal actions. Specifically, we train the user model to explain the actions the user took. We model the likelihood of the user taking a particular action given a history of observations and past actions by marginalizing out the state. This involves computing a near optimal policy for the completed task and representing the user's beliefs using a parametric model, for example, a neural network. We train our model of the user's state estimation process using a maximum likelihood objective over the demonstrations. In our experiments, we considered two types of tasks. Tasks in which we assume prior knowledge about how the user's state estimation process is flawed, and other tasks in which we don't know the user's biases upfront and need to learn a model instead. We look at MNIST and car racing game domains in which the user's perception is bandwidth constrained, or subject to intermittent delays in the arrival of new observations. We also look at a lunar lander game in which we might expect the user to consistently underestimate certain state variables, but we aren't quite sure about when or to what degree this actually occurs. In the first set of experiments, we assume the user is primarily affected by limited sensor bandwidth. Consider the navigation with visual impairment setting described earlier. The assistant might detect many different objects in the scene. But if the assistant were to simply tell the user about all of them, the user would be overwhelmed and may not be able to incorporate the new information and move toward their target. A simple initial solution to this problem is to inform the user about just one of the visible objects selected uniformly at random at each time step. The problem with this method is that it may end up providing the user with uninformative observations about common objects that happen to be found throughout the house, and hence do not help the user figure out where they're standing. So while the user does get some information, they may still be unable to make good decisions. Our method optimizes the assistant's choice of which object to inform the user about at each time step. By telling the user about landmark objects that can only be seen from the user's current position, the assistant induces more accurate beliefs in the user, which then leads to more optimal user actions. We ran experiments with simulated users navigating a simulated indoor environment. The guide can see the user's egocentric scene, but the user cannot. The guide can also determine which objects are present in the scene, and in the baseline condition, simply selects one of them uniformly at random to tell the user about. The user receives this categorical observation of an object from the guide, then looks up all known locations of that object throughout the house in their mental map of the house. The user then updates their beliefs about their current position and orientation, and attempts to move along a shortest path to the goal. Our method improves upon the default guide by optimizing the choice of object information to give the user. This tends to result in more accurate user beliefs and, as a result, the user taking less time to reach their goal. We also ran an experiment with 12 human participants classifying images of MNIST digits. We revealed one row of pixels at each time step and asked the user to attempt to label the image at each time step using only the pixels revealed so far. In the default condition, pixels were revealed from top to bottom in order. The user tends to take a while to correctly identify the digit this way, since informative pixels tend to be evenly distributed throughout the image, including near the middle and the bottom. In another baseline, we reveal the pixels in a random order, which happens to be a good strategy in the long run, but doesn't necessarily reveal informative pixels early in the episode. ACE, on the other hand, tends to quickly reveal rows near the middle and rows with many non-zero pixels, enabling the user to more accurately guess the label earlier. Here's a step-by-step comparison of the two baselines in our method. When only 25% of the image has been revealed by time step 6, the pixels revealed by ACE make it much easier to guess that the digit is a 3 compared to the other two baselines. In the user study, we found that our method substantially outperformed the top to bottom baseline and enabled the user to guess the label earlier using fewer pixels than the random baseline. Now that we've looked at two domains where we know the user is bandwidth constrained, let's look at a different domain where the problem is not bandwidth, but rather intermittent observation delays. In this real-time driving video game, at each time step, the user receives an image observation, processes that observation, and chooses to steer the car left or right. They then get a new observation and repeat. Unexpectedly, the environment does not provide a new observation at the next time step. Instead of showing the user a blank screen, the default interface simply copies the previous image and shows it to the user again. The problem with this method is that the user may not be able to incorporate the delay into their state estimation process, and as a result, may take too long to react to time-sensitive situations, like approaching a left turn. In practice, even when users could clearly tell there was a delay in the user study, they still weren't able to adjust their actions to deal with it. Instead of copying the last observation, our method constructs a synthetic image observation that is representative of the assistant's belief state. Showing the user this prediction of the current observation enables the user to better estimate their position, orientation, and speed, which in turn enables them to make time-sensitive decisions. Here are some videos from the user study. On the left, you can see the video feed periodically getting stuck due to observation delays. In the middle, whenever the true video feed drops out, the assistant fills in the missing frames with predicted images. The predictions tend to match the ground truth more closely than the default delayed images. Users tended to drive on the road and stay off the grass much more often when they played with the assistant's predicted video feed than when they played with the default delayed video feed. In our third set of experiments, we had human participants play a variant of the lunar lander game, in which we deliberately made the lander difficult to see, but added a horizontal bar to help the user perceive the angle and position of the lander. We set up the game to let the user focus on keeping the lander level as it descends, using the left and right keys to control the lateral thrusters that rotate the lander clockwise and counterclockwise. What made this game a bit different from navigation and driving is that we weren't quite sure how the user's state estimation process would be biased. We knew that estimating the lander's current angle might be difficult, but we weren't sure exactly when or to what degree this would be the case. In the default interface, we simply rotated the tilt indicator to match the lander's true angle. The problem with this is that while it's easy to tell when the lander is severely tilted, it's harder to tell when the lander is only slightly tilted. And this can be a problem for the user, since keeping the lander level requires detecting tilt early when it's still small, so that the thrusters have enough time to force the lander upright. By collecting data of the user's actions with the default interface, our method learns a model of the user in which the user underestimates the lander's angle. This leads to an assistance policy that rotates the tilt indicator past the lander's true angle in order to exaggerate the tilt, which is then easier for the user to detect. As a result, the user tends to respond earlier to even small tilts. Here you can see the assistant exaggerating the tilt indicator, which is especially helpful early in the episode. Users who were shown the exaggerated tilt indicator were able to keep the lander level more often than users who were shown the default interface. Our method learned a different angle distortion factor for each user. For users who performed reasonably well with the default interface, it learned to only slightly exaggerate the angles. For other users who performed poorly with the default interface, it instead learned to swing the indicator wildly to indicate tiny changes in the angle. Thanks for listening. You can read the full paper, watch more videos, and access our code from the project website.